Okay, here we are with chapter 3. So in this chapter, we're going to be looking at derivatives and how we can use derivatives to do some curve sketching. And so we're going to start off with our first section called increasing and decreasing functions. So we're going to look at how function increases and decreases. So given the graph of f of x equals x cubed minus 4x, and its derivative, answer the following. Okay, so here's a graph of f of x, and the dotted line represents the derivative. Okay, and we can tell that because the f of x is a cubic function, cubic polynomial, and we have those two turning points there. And its derivative would be 1 degree less, which is quadratic. So the dotted line looks like a parabola. So question A asks, when is f of x increasing? So if we look at f of x, we can see that it is increasing, meaning the y values are going up. So it is increasing along what I'm highlighting here, from the left all the way up to this point. And then afterwards it's decreasing. And then after this turning point down below, it's going to be increasing once more. Okay, so I can express that as an interval, and I'm going to say that's the interval from negative infinity to, and it turns out that point, that turning point, there's negative 1.15, as well as the interval from 1.15 to infinity. Okay, and so yeah, if you're not sure how do we get negative 1.15, just think of, okay, the derivative f prime x is 3x squared minus 4 using the power rule. And if I solve for f prime x equal to 0 and solving for x, so again, this is where the slope of the tangent line at those points is 0. Okay, that's what I'm looking for. When is f prime x equal to 0? And if I solve for x, I get the square root of 4 over 3 equals x, plus or minus. Okay, and so that is 1.15. And my intervals, I am not including the endpoints. Okay, notice how I use round brackets. So we're not going to be including the endpoints by convention here. When is the graph decreasing? We can see that it's going to be from negative 1.15 to 1.5. And that's highlighted in blue. So the interval is negative 1.15 to 1.15. Okay. And I guess, again, round brackets, because at the endpoints, it's a turning point. We don't see the graph either increasing or decreasing. So we're not including the endpoints. What is true about f prime x when f of x is increasing? Okay, so f prime x, when f of x is increasing, we notice that, so for the yellow portions here, okay, let's just divide the interval there, okay? So for the yellow portion of f of x, the graph of the derivative, this part here first, and on the other side, it's this part here. Okay, we notice that thing I'm highlighting in red, those portions of the parabola are positive y values. So I can say here that f prime x is positive. Okay, in other words, the y values are positive. Okay, what about when f prime, what is true about f prime x when f of x is decreasing? Well, if I look at f of x highlighted in blue, the derivative is this portion of the graph, okay, the dotted line, and those values are negative. So whenever f of x is decreasing, my derivative takes on negative values. F prime x is negative. Okay, I'm saying that the y values are negative. Okay, and where is the tangent line horizontal for f of x? What do you notice about f prime x at this point? So I've established that, hey, the horizontal lines where the slope is 0, we can see that f prime x at those two particular points are right here and here. f prime x is equal to 0. Okay, so at x equals negative 1.15 and 1.15, f prime x is 0 at these points. Remember, the slope of a horizontal line is 0. Okay. So that brings us to intervals of increase and decrease. You can say that a function f is decreasing if for any value on the interval, the successive y value is less than the previous y value. And we say the function f of x is increasing if for every successive y value is greater than the previous y value. Yeah, then it's increasing. Okay, so a simple definition of increasing and decreasing functions. Now, where the derivative comes into play, for a function f that is continuous and differentiable on some interval, we can say that f of x is increasing if its derivative is positive in that interval. Okay, and f of x is decreasing if its derivative is negative on that interval. And we can see that here, right? So if I look at an increasing function, its derivative as I go from left to right is increasing. The slope of that tangent line is getting steeper and steeper and steeper. For a decreasing like a function, the slope of the tangent line is decreasing, right? So it's getting the steepness is getting less and less and less. Okay, so that is an important thing. We've got to know to connect derivatives with their functions. Now, to get them algebraically, we do need to understand where do these turning points happen? Where do the graphs change from positive to negative and vice versa? And before we get to that, we do need to just get an understanding of how to find the derivative, and what value of x is the derivative equal to 0. So here I give you a couple of derivative functions. What value of x makes that derivative 0? And it's just simply plugging in 0 for the derivative and solving for x. So 0 equals 3x minus 15. Adding 15 to both sides, so 15 equals 3x. And so x equals 15 divided by 3, which is 5. And for g prime x, you have g prime x equal to 0. Okay, so 0 equals x squared minus 5x minus 24. We have a quadratic to solve here, so it might be a good idea to see if we can factor this. And indeed we can. It's a simple trinomial. X minus 8 and positive 3 will give me 24 when I multiply them. And when I add them, I get negative 5. So x minus 8 and x plus 3, revealing the x values are a positive 8 and negative 3. So at positive 8 and x equals negative 3, the derivative is equal to 0. Okay, so you try, take a moment, pause the video, you try the one on the right-hand side. Okay, so hopefully you had a chance to try that. So when you set that equal to 0 and you factor the left side, we get 2x minus 1 and x plus 3. And solving for x, we get x equals 1/2 or x equals negative 3. Okay, all right, so let's go on. Intervals of increase and decrease. All right, so we have a function. Determine the intervals of increase and decrease. F of x equals x cubed minus 3x plus 2. And I give you the graph right there. Now, I know I can get the information I need from the graph, but I also want to show you algebraically how we determine this. So let's just look at the graph first. If I look at the graph, we have a turning point. So at x equals -1, we have a turning point up there. If I drew a tangent line, that would be a horizontal tangent of 0, a slope of 0. And at x equals 1, I have another turning point. And if I drew a tangent line there at that point, the slope of that tangent line would also be 0. It's a horizontal line. Okay, so we have these things we call critical points at -1 and 1. And we can say, we can use that to determine, hey, with the graph's increasing and the intervals, that those critical points will help us determine how to segment our intervals. Okay, but algebraically, I wanted to show you this. So to do this algebraically using derivatives, we first start with finding the first derivative. F prime x equals, power rule says 3x squared minus 3. Okay, and if I know my critical points have a horizontal tangent line, and the slope of that line is 0. That's the same as saying, well, make the derivative equal to 0, because the derivative is the slope of that tangent line. So if I made the derivative 0, and 0 equals 3x squared minus 3, and I solved for x, what I would get is, well, add 3 to both sides, 3 equals 3x squared, and then divide both sides by 3, I'll get 3 over 3 equals x squared. 3 over 3 is 1, and then if I take the square root of both sides, don't forget you're going to have a plus and minus. Square root of 1 equals to x, or we could just say x equals plus or minus 1, and there they are. Those are our critical points, plus and minus 1. Okay, now the remaining procedure for the rest of the solution would be to do something like this. I'm going to say here, x equals 1 and negative 1 are critical points. Okay, and we're going to segment them into intervals. So if I know the turning points or critical points are where the changes from increasing to decreasing or decreasing to increasing happen, then I'm safe to create these intervals. So I'm going to create the interval from negative infinity to negative 1, and then from negative 1 to 1, and then from 1 to infinity. Okay. And my table, I'm just going to put something on the left side here. I'm going to just put 2 more rows, f prime x and f of x. Okay, and so what I'm going to do is I'm going to use test points to determine intervals of increase or decrease. Okay. So let's say from negative infinity to negative 1, if I pick a test point of negative 2, f prime of negative 2, and I plug that into the derivative says, okay, 3x squared minus 3, so negative 2 squared minus 3 equals 4. Let me just make 3x squared minus 3, so 3x squared minus 3, so 3 times negative 2 squared, which is 4 times 3, which is 12. 12 minus 3 is 9. 12 minus 3, which is 9. Okay, and that says the derivative in that interval is positive if I use a test point. And if the derivative is positive, that says my function must be increasing. Okay. All right, if I use the next interval, negative 1 and 1, I'll just use a test point of 0. So f prime of 0. If I plug that into the derivative, so it'll be 3 times 0 squared minus 3 equals negative 3. So that's going to be a negative value. Okay, and if the derivative is negative, according to the previous page, we've established that, hey, the function is decreasing. And from 1 to infinity, if you use a test point such as 2, we'll get positive 9, and that is increasing. And in between these intervals, we do have a slope of a horizontal tangent turning point, slope of 0. Okay, but this table is what we use to demonstrate, hey, where are our intervals of increase and decrease? And then we can just verify that with the graph. Hey, we have an increasing function from negative infinity to negative 1, then a decreasing function from negative 1 to 1, and increasing again from 1 to infinity. Okay, so try the next one on your own. Pause the video and see if you can do it. Okay, hopefully you had a chance to try it. Here it is, f prime x. Find the derivative first. Using the chain rule, we'll bring the 2 to the front. 2 times x minus 3. Exponent becomes 1, but we don't write that. And then the derivative of the inside, which is just still gonna be 1. And if I expand this, I get 2x minus 6. Now, solving for critical points, make the derivative equal to 0. 0 equals 2x minus 6. And solving for x, I get x equals 3. So we can only create 2 intervals here. So create a quick table. We have one interval that says the interval that's everything below 3 and everything above 3. Okay, and I'm going to just use, again, write down f prime x and f of x. Use a test point for everything below 3. I'm going to just try f of 1. What is f of 1? Well, let's put that in there. F prime at 1 equals 2 times 1 minus 6, which is a negative 4. Okay, and so if it's negative, then the function is decreasing. And if I looked at every value on the other interval x greater than 3, I'll use a test point, such as +4. You don't have to make a complicated test point, just pick the nearest one, integer value, right? So f of 4 equals what? Well, f prime. I should make these prime. Did I put that in the other table? I did, yeah. So I just forgot to put the prime. F prime 1, F prime 4. So F prime 4 is equal to 2 times 4 minus 6, which is +2. And that positive derivative tells me that the function is increasing. And so there you go. Without having a picture of the graph, you can now determine intervals of increase and decrease. Let's look at a more complex example on the next page. For the function x to the power 4 minus 8x squared minus 7, determine the intervals of increase and decrease. Okay, so we are going to start with the derivative. So f prime x, power rule applies here. So if x to the power 4 becomes 4x cubed, minus 8x squared becomes minus 16x, and minus 7 just disappears. Okay, now I'm going to solve for the critical points. So again, set f prime x equal to 0 to find critical points. Okay, and so that's what I'm going to do here. And I know we have the picture of the graph. That's going to help us verify some of it, but we can't really. Okay, so it's 0. We can use the graph. We can expect to know what to find the answers, but I want to show you algebraically what that looks like. Okay, so set this equal to 0. 0 equals 4x cubed minus 16x. Solving for x, let's see if we can do some common factoring first. I can probably take out a 4 and an x from each term. So 4x times x squared minus 4. Okay, and we can probably see that x squared minus 4 is a difference of squares. Okay, if it's a difference of squares, I can factor that further. 4x times x minus 2 times x plus 2. Okay, and now we can solve for x. We have 3 values for x, so solving, we have x equals 0, x equals 2, and x equals -2. Okay, and as you can see, we can verify that in the graph. We have where the derivative is 0, the horizontal tangent line at -2, 0, and +2. Okay, so I'm going to create my interval chart. Yeah, let's give that a formal name. Create an interval chart. Okay, let's just use a ruler because we're going to create several intervals. Our table's going to be a little bit bigger than the rest, the previous examples. Okay, I'm going to have 4 intervals. If I have 3 critical points, it's going to create 4 intervals. So let's create some columns here. All right, 1, 2, 3, 4, 5. Okay, so here we go. I'm going to create the interval from let's see here, 0 to -2. So the interval from -infinity to -2, the interval from -2 to 0, the interval from 0 to 2, and the interval from 2 to infinity. Okay, and then you're going to use test points to find f prime x at a single test point from each interval. Okay, so let's use some test points here. Let's just look at the first interval, -infinity to -2. What if we used -3? So f prime of -3. If I plugged in -3 into my derivative, I'm going to have to write here. So what did we say? So 4 times x. So 4 times -3 is -12. I'm following 4x times x minus 2 times x plus 2. Let's just use the fully factored form. So -3 minus 2 is -5 for the second factor, and then -3 plus 2 is -1 for the third factor. And even without paying attention so much to the numbers, I can expect a negative result because I'm multiplying 3 negative numbers. So it's -60 is the result, but I don't care so much about the 60 part. I just care that it's negative. So my interval chart, I'm going to say, hey, the derivative is negative in that interval. So my function f of x is decreasing from negative infinity to negative 2. For the next interval from negative 2 to 0, the test point maybe I can use is negative 1. And again, this is all arbitrary. You pick any test point in that interval. So for negative 1, I have 4 times negative 1, which is negative 4. X minus 2 will result in negative 3, and x plus 2 results in positive 1. Two negatives and a positive make a positive. That is 12, but I don't care about the 12. I just care that the derivative is positive. And so the function is increasing from negative 2 to 0. And then for the next interval, 0 to 2, I'll just pick f prime of 1. Okay, and plugging in 1, I'm going to get 4 times 3, and sorry, 4 times negative 1 times 3. And that's going to be a negative 12. So the next interval is negative, and the function's decreasing. Okay, and then the final interval from 2 to infinity, I'll pick maybe 3, f prime 3. You can pick 3, you can pick 4, you can pick 10, whichever. 3 times 4 is 12. X minus 2 makes it 1, and then x plus 2, 3 plus 2 is 5. So 12 times 1 times 5 is 60, positive 60. All I care is that it is positive. The derivative is positive, so the function is increasing. Okay, sometimes maybe you want to write here decreasing, increasing, decreasing, increasing, or you can just use the arrows to indicate if it's decreasing or increasing. Okay, so even as a concluding statement, therefore, intervals of increase are negative 2 to 0 and 2 to infinity. And intervals of decrease are negative infinity to negative 2 and 2 to infinity. Okay. Sometimes questions may ask you, what are the intervals of increase? Only increase, not the decreasing ones. Just what are the ones that are increasing? Or maybe they're going to ask you for what are the intervals that are decreasing, or both. When you're doing overall curve sketching, you'll want to find out both anyways. So that's how we do that. Okay, and then we can verify our results. Again, we have the graph. If you're doing homework, you can always check on Desmos. If you're given the function, you can graph it just to check. And yes, we can see here that we have a decreasing function until negative 2, increasing until 0, negative 2 to 0, and then 0 to positive 2 to decreasing, and then increasing from 2 to infinity. Okay, let's look at another example. Given the graph of f prime x, state the intervals of increase and decrease of f of x. Draw a possible graph of f of x. Okay, so this is different in the sense that I got f prime x here. This is not f of x. Don't get confused. This is the derivative. The derivative looks like a parabola. So the function, the original function might be a cubic function, right? But you start off as we've been doing, right? When is f prime x equal to 0, right? That's the question. Where are the critical points, right? So it's going to be here at 1 and here at 3, right? So again, if you confuse this for f of x, you're going to be looking for like a turning point with a slope of the tangent, horizontal line. But this is not f of x. This is f prime x. This is the derivative. So look where is the derivative equal to 0? And that's a y value. Remember, that's a y value. 0. Where is the derivative equal to 0? It's at x equals 1. I'm gonna write that down. X equals 1 and x equals 3. Okay. And in other words, I'm trying to let's put this in our notes. The y values of f prime x is or are 0. Say r plural. Okay. Are 0. All right. So the intervals are, what are the intervals? Well, let's draw our interval chart. Okay, I'm going to say the intervals from I'm going to have an interval from 3 to infinity, then an interval from 1 to 3, and then everything below 1. So negative infinity to 1. And if I look at f prime x and f of x, pick a test point, negative infinity to 1. Well, we can see all the y values of the derivative are negative. And so the function f of x must be decreasing. From 1 to 3, all the y values here are positive. So the graph must be increasing in that interval. And then from 3 to infinity, all the y values in the derivative are negative. So the function f of x must be decreasing in that interval. Okay, so I can say here, f of x is decreasing from negative infinity to 1 and 3 to infinity. And f of x is increasing from 1 to 3. Okay, now the I guess, yeah. And now the question is, can you draw a possible graph of f of x? There are going to be many different kinds of graphs that that this derivative could serve for an f of x function, right? So there's going to be many possible f of x functions that would work. So just have to create one possible f of x, just following the interval chart. So from negative infinity to 1, I have a graph that's decreasing. And then at 1, I have a turning point. So at 1, I can even put a point somewhere. It has to be a turning point, so it has to look something like this. Okay, it goes from decreasing to increasing. And then at 3, I could have another turning point that goes from increasing to decreasing. Okay, something like that. And here's a possible function, cubic polynomial, right? Okay, so something like that perhaps could be what we're looking for. Okay, so it's you wouldn't know the precise f of x unless you had more information, like a given point or another condition to do that. All right, so that is it for the first part of the lesson. The main idea is, so the first section of this chapter is, the main idea is just, can you identify where are our intervals of increase and decrease based on the sign of the derivative? Okay, so just remember that when the derivative is positive, then your graph is increasing. And if your derivative is negative, your graph is decreasing. All right, so you can have a look at the practice problems I assigned for this section. Okay, and so the assigned practice problems are on page 156, numbers 1, 2, 4 to 11. Okay, and then when we reconvene the next class, we'll just continue on with 3.2. Okay, that's it.